Hi, today we're going to start talking about structures, and in particular we're going to start looking at a structure called a truss. A truss is a structure that derives its strength from having its members arranged in triangles. Well, why triangles? Why does it matter that they're arranged in triangles? Well, let's make a couple of assumptions first. First thing we're going to assume is that our members are not going to significantly change in length. So the member that we put in place in any kind of a structure, we're assuming it doesn't change in length at all. And the second assumption we're going to make is that our members will actually completely freely pivot, just like this set of members I have right here. They will freely pivot one relative to another. Another way of putting that is to say that one member will not react a moment onto the other member. So again, the question is, what is it about triangles? Why is it that a triangle makes a strong structure? Well, to answer that question, why don't we take a look at a quadrilateral and then look at a triangle and see how they might be different. So here I have a triangle and here I have a quadrilateral. Now the main question we need to ask ourselves is, how many shapes can we make with the quadrilateral without violating one of the rules that I gave us? Remember, the rules were we can't change the length of the member, and the other rule was that the members can pivot one relative to another. If you look at that for a quadrilateral, if the members are allowed to pivot one relative to another, even without changing length of any of the members in that quadrilateral, the structure you will be able to see here has infinitely many different types of shapes that can be made as a result of just changing the angle between a couple of the members. All right, contrast that with a triangle here. A triangle does not have that mobility. You cannot move it and change the shape of the triangle without actually changing the length of one of the members. So what we actually have here is with a triangle, we're making a unique shape that cannot change unless we violate one of the rules that we had set up. Alright, so I guess the next question is there something we can do about this quadrilateral? Well, there is. We can actually stick a member across the diagonal of the quadrilateral, and you'll see there that if you do that, it actually changes this structure into two different triangles. And you'll see there that now that structure only has a unique shape. So it's made entirely of triangles. So it's lost that mobility, which in this case is something that we were trying to do in order to make that structure more rigid. All right. Now this actually is all by itself a truss. It actually is this structure that derives its strength from having its members arranged in triangles. But I guess the next question is, a lot of times we haven't seen trusses that look exactly like this. Why not? Well, a lot of trusses actually take more triangles than just this, and it stretches out over an entire span, let's say. A lot of times you'll see these on bridges or on roofs. Whenever you see it like that, basically what you're seeing is that usually they're trying to cross some kind of a span where it's supported at its ends, but not supported in the middle. And so let's take a look and see what we can do to actually extend the length of this truss just a little bit further. All right, and here is what we can do. We can actually just stick a couple more members on there, like so. Stick one on there, stick another one on here, and what we start to see is something that if you were to ask someone what a truss was and they had any concept of what structures were like, this is something like what they might tell you it looked like. That looks kind of like a bridge, and a lot of people have heard of a truss bridge, and so they might say that what we've created there is a truss, and it is. All right. Let's look at a couple of different ways that you can take a truss and put it across a span. All right. This is a truss. Of course, the last one I showed you was also a truss, but this one is a truss. And let's see how you can put that across a span. So let me set up my span here. All right. In this case, my span will be formed by some wicker boxes. All right. And we're going to look and see how this truss can actually go across that span. All right. The way I'm showing you how it's going across right there, you may say, well, why is he putting it up there that way? Well, There are certain trusses that put the structure down below the level of where you might think of this as a roadway, but really it can be anything, any kind of a load that you're trying to support across that span. You could apply it to this top piece. You actually could apply it to the bottom piece as well. But I could either put this truss this way, which you may not be as familiar with that as seeing what the trusses that are put up like this. Imagine here that this is a river. The reason why you're probably more accustomed to seeing trusses upward like this is that what this does is it puts more clearance between the bottom of the structure and the surface of the river. And so what you'll see there is that this is actually more advantageous if you need to have boats or other type of water traffic going underneath this. If you have a really tall boat, it might be hindered if your structure was sticking downward, whereas when it's sticking upward, it's completely out of the way. So there's an introduction to some of the stuff that we're going to talk about. These trusses can be analyzed if we continue to make those assumptions that I started off saying, that the members cannot change in length and or significantly change in length anyway, and that the joints do not react significant moments between one member and the other. That'll allow us to actually analyze these trusses, and that's what we're going to talk about today.
A truss is a structure that derives its strength from having its members arranged in triangles. Let's look at some of the other assumptions that we're making when we do these types of analyses for these trusses. So here we're going to be talking about assumptions. Okay, the first assumption that we're going to make here is that our truss's members are going to be connected using frictionless pins. Alright, and this is important because we can't be having one member react a moment to another member. Alright, the second assumption we're going to make here is that the members, each member is going to be connected only at 2 points. Okay, and then finally we're going to make the assumption here that the members are not going to be loaded anywhere else but at a joint. Okay, and so what this would actually include, we're going to say that the members, we're going to assume they're massless, and basically what that means is that even self-weight would be included as far as being loaded anywhere but in the joint. Alright, and then finally, the last assumption that we are going to make here is that the members do not significantly change in length. Alright, and the reason that's important is if the members were allowed to change length, basically what that would mean is that the truss could actually change its shape, and if it changed its shape, then that would actually change all the angles between one member and another, and that would actually start changing what our analysis was. So we're going to make that assumption as well. The consequence of these first three assumptions here, which are kind of the key, the consequence of those is that every member in a truss can be thought of as a two-force member. Alright, and that's a key word right there, or a phrase, a two-force member. Well, what do we mean by a two-force member? A two-force member is literally a member that only has two forces on it. Okay. Now remember, we're in statics here, and so if we have a member that's only got two forces on it, one of the results of that assumption there is that we either have a member that has two forces that are collinear there, that pull opposite each other, and by doing that, that keeps our member from accelerating. Or the other possibility is that we have a member that instead of having a tensile load on it like I've shown there, our member can also have a compressive load, so we can have a load that kind of pushes inward on this. But these are the only two possibilities that we can have for our truss members. If we have anything other than this, that actually ends up making it something like a three-force member, and that is not allowed. We can't have that. We also can't consider the self-weight of the member because that would essentially do the same thing. But the consequence here is that we've got all these two-force members, and by having the two-force members, that allows us to draw free body diagrams of pins and do concurrent force system analysis basically on each pin. Alright, so now that we kind of know what the assumptions are for our trusses, let's look and see. Probably the best way to learn how to do this is by doing an example. So let's go ahead and start with a physical scenario like I've shown here. We have a 10-pound weight hung from the middle of a fairly simple and fairly symmetric truss here. Alright, so step one, basically this is the way we will always start this problem, or these types of problems. I suppose not necessarily always, but very frequently we are going to start these problems this way. We need to find the external reactions. Alright, and so the way we find external reactions, we can do a free body diagram of the whole entire structure. Alright, we can keep in mind here that this whole structure is actually all in equilibrium, and so at this point we can leave it all together and do a free body diagram of the whole thing. I am going to make it just a little bit simpler when I do this free body diagram and not show the size and the shape of each one of the members. Alright, I'm just going to kind of simplify it down to where the whole structure looks kind of like this. Alright, and we're going to understand that that's all one rigid structure that is not moving one piece relative to the other piece. Alright, the reactions that we have over here, alright, and I'll call that, we'll call this point A over here. May as well label all these points here, A, B, C, and D. The reactions that we can have at A, actually we have two components of reactions that are possible at A, and the reason why is that we have a completely pinned joint there at A, so it's not allowed to move in either direction. So we'll put those on there. We'll call this RAY, and this we'll call RAX. Alright. Instead of showing a 10-pound load as a weight hanging there, I'm going to go ahead and just show the force here. That's a 10-pound force acting right there. And the roller that we have there at C, that roller actually can only put one component of reaction at that pin at C, and so we'll call that RCY. Alright, and this is essentially all the reactions that we've got on that free body diagram. The critical dimensions that we need to know here, we need to know that this is 4 inches across from there to there. We need to know that that's another 4 inches across from there to there in order for us to use this free body diagram. Alright, so that's there. And then to make it complete, we'll go ahead and stick some axes on here also, our X and Y axis for those two things. And once we get that free body diagram down like that, what we can do is we can sum moments for that free body diagram. And we're going to sum moments, I guess, at A, and we're going to take counterclockwise to be positive. When we do this, we'll find that we have our 10-pound load that creates a clockwise moment about A, which is actually a negative moment there, based on the assumption that I made. So 10 pounds, negative 10 pounds times 4 inches gives the moment that is created about point A. And then we'll have our reaction at C that also can create a moment about point A. And it tends to rotate in a counterclockwise direction. So we're going to take that as a positive RCY times its distance from A, which would be 8 inches. Alright, and all that is equal to 0. Okay, so now that we've done that, we can actually simplify this and figure out that RCY is equal to 10 pounds times 4 inches divided by 8 inches. All right, and this just tells us that the reaction at C in the Y direction is just 5 pounds. Now, you might have been able to do that just by inspecting it, but I figured I'd go through the process of going ahead and finding that reaction. The next part of that is just summing forces in the Y direction. We'll take upward to be positive there, and there we'll have 5 pounds due to the reaction at C. We'll have 10 pounds due to the force that's applied there at joint D, and then we'll have another RAY that's applied upward at A. All that's equal to 0, and based on that, we can then calculate that RAY must have equaled 5 pounds also. Okay, so again, in this particular instance, that's probably something you could have gotten easily, but figured I'd go through the process anyway. Alright, now that we've got our external reactions for this body, we're ready to move on to the next step, and that is to do free body diagrams of the joints to figure out how much force is in each one of the members. Alright, to do this, if we are judicious about which joint we do first, it actually makes the math a lot easier. What you want to look for is you want to look for joints where you have 2 or fewer unknowns. Alright, at the joint at B, I would say we have 3 unknowns, basically, because at B we have these 3 members and we don't know the force in any one of those members. At D we would also have 3 unknowns, but at A and at C we would only have 2 unknowns. Alright, and so tell you what, let's go ahead and just pick C and do a free body diagram of the joint at C. Alright, so there I'll draw the joint. It's not a complicated drawing. It's just basically a dot, but there's our joint. We have our external reaction of 5 pounds that happens on that joint. Then we have forces that also act on that joint. We have a tension. We don't know that it's a tension, but we can assume that it's a tension that happens in member CD. All right. We also have the force that happens in member BC, and so we'll stick that up here. And basically, what we need to do here is, I guess I need to talk a little bit as far as why we know the directions of those forces. Those forces, since these, in this truss, we've met all of our requirements. We have our members only connected at 2 points each with frictionless pins, and so we already know the direction that happens as far as the force in those members. All right, and so that's good. To make this a complete free body diagram, we'd want to put some indication as far as the direction of that force. We can do that using a slope, basically. We have a run of 4 for a rise of 3 based on these values of 4 and 3 in the original scenario. This would lead to the idea of a hypotenuse there of about 5, not about 5, exactly 5, because that's a Pythagorean triple. All right. We've got here, let's make it complete by putting coordinate axes on there, and so that's good. Once we do our free body diagram like this, what we're ready to do is write equilibrium equations. So we'll go ahead and start that. We'll sum forces in the x direction first, taking rightward to be positive. And we'll see here we've got TCD that acts in the negative direction, so we'll have there negative TCD. And then TBC, its x component, also acts in the negative direction, so we'll say minus TBC. All right, and we only need the x component of that, and so we're going to stick a value of 4 over 5, because that's the ratio of horizontal to hypotenuse, and so that's essentially the same as taking the cosine of the angle of that thing. All right, and all that's equal to 0. Those are the only 2 forces we have that have x components. Well, that equation, we can't solve that right away, and so we need to move on to our next equation, where we will sum forces in the y direction. And we'll take upward to be positive for that. When we do that, we'll find that we have this 5-pound force that acts upward. That's due to that external reaction. And then TCD has no vertical component, but TBC does have a vertical component. So we'll take that TBC, it acts generally upward. All right, and we'll take the ratio of 3 over 5 to get just the vertical component for that force, and that's all equal to 0. So what we end up with there, if we solve that, TBC is actually equal to, we would have 5 pounds times 5 over 3, which actually is just equal to 8.33 pounds. All right. Well, now that we have that, we can then plug that into our equation that we had up there, and if we do that, we'll find here that this is minus TCD minus 8.33 pounds times 4 over 5. That's equal to 0. And I just noticed something here. We actually made a mistake here. We need a sign of negative there, which makes that a negative 8.33, which then it makes this a positive right here. And after doing that, we find that TCD is equal to 6.67 pounds approximately. All right, and so what we'll see there, both of these values are less than the applied force. This is one of the reasons we use trusses. So based on our last analysis, we now know the forces that are in a couple of these members. We know that the force in here in member BC, we know that the force there is 8.33 pounds. This negative value right there basically means that this is in compression. All right, remember, we assumed that it was going to be in tension, so the fact that it comes out negative basically just means it's in compression. All right, here our value came out positive, so we know that that one is actually in tension. All right, and I've actually shaded in here the members here that we now know. All right, so we know the forces in those members, and so I've also here updated this, and so at D we now only have 2 unknowns. We only have those 2 members left there, AD and BD, that we don't know the forces in there at D. And so let's go ahead and take that joint at D and do a free body diagram of that joint, all right, and use that to figure out those forces that we don't know there. Okay, right there at D, we know that we have a force that acts in the downward direction due to that 10-pound load that we're applying. All right, we would also see that we have a what we'll call TBD. That's the tension in member BD. Again, we're assuming a tension, and if it comes out negative, that means that we assumed wrong. All right, so we've got that, and then we've also got these 2 forces, TCD and TAD. All right, so that's actually a relatively simple free body diagram right there. We'll go ahead and make it complete here by putting our coordinate axes on there. All right, and now we're ready to do equilibrium equations on that diagram. All right, so doing this, we'll go ahead and take the sum of forces first in the x direction, I guess. All right, and when we do this, we'll find that we've got our TCD that acts in the rightward direction, so that's positive, and then TAD that acts in the negative direction there. All right, and so those sum together equal 0. But remember, we know that TCD from up here, TCD is just 6.67 pounds. So we can go ahead and stick that in here. 6.67 pounds minus TAD is equal to 0. And what that means is that TAD is just equal to, again, 6.67 pounds. All right, and so we now have one more unknown that we know there. Okay, and then finally, we'll go ahead and do a sum of forces here in the y direction to figure out the force that we have in BD. All right, so there we've got our negative 10 pounds, that's the applied load right there, plus TBD is equal to 0, and based on this, TBD is just equal to 10 pounds. Both of those are positive, which means that both of those are in tension. All right, and so now we know 2 other members here. And let me go ahead and I'll just shade those in now. We know the forces that are in two other members. So we're really making some pretty good progress on this truss. We now have basically all but one of the members figured out as far as how much force is in each one. So now we have some more information about this truss. We know that the tension in BD is 10 pounds, and we know that the tension in AD is 6.67 pounds. And so really the only other member that we need to solve for is member AB. We can do that based on a free body diagram of, of a joint at A, or we can do it of a joint at B. Either way. I guess I'll just pick randomly here to choose the point at B. I'll go ahead and draw that free body diagram, and then we're going to show the forces that act on that. We have a tension here in BD. We know that that's 10 pounds, so we'll put that in there. We also know that we have a force in BC, and that acts in this direction. All right. Now remember up there, the force in BC was negative. All right, but what we need to keep doing is keep on assuming these tensions, because if we're going to assume a tension, then that ends up to be a negative value. All right, so we can show the arrow that way, and then we can show it here as a negative 0.8 or 8.33 pounds rather. All right, and then finally we've got this force that acts down like this, and this is the tension in AB. All right. It's good practice to put some coordinate axes on here, so we'll go ahead and do that. That's X, and that's Y. All right. Also, we should probably put in here some information about what direction these things go. All right. Again, this is a slope of 4 to 3, and that's a distance of 5 right there, so that's handy. And then we'll go ahead and put in the same kind of information over here. That would be 3, that's 4, and this over here would be 5. All right, and so now that we've got that free body diagram, we can go ahead and we can solve for some of the unknowns here, or one of the unknowns, the only unknown being TAB. All right, so writing our equilibrium equation here, we'll sum forces in the x direction, and we'll take rightward to be positive, so we'll sum that. And here we have a negative TAB, and we just want the x component of that, so we'll take that and multiply it by 4 over 5. All right, and then we have this negative 8.33 pounds. All right, that acts in that direction. So even though it's in the positive direction, that negative comes through there, and we have negative 8.33 pounds. All right, times, we just want the horizontal component of that, so we'll take that times 4 over 5 also. That's equal to 0. And what we'll notice here is, due to the symmetry of this whole thing, these actually can just divide out, and we'll notice that TAB is actually exactly equal to TBC. All right, so TAB then is also equal to negative 8.33 pounds, which is good, because, and we really hoped it was going to show up that way, because if it didn't, then that would mean that even though our truss was symmetric, it would give you a different value for the two sides, and it'd be hard to explain why that was the case. So I'm glad that it ended up this way. So that's good, and we like that. So. All right, we've actually solved for pretty much everything here. We've got all, let's see, 1, 2, 3, 4, 5 members here. We've got all 5 of those forces and all those members solved for. So you might think we're done, and we basically are. But the last thing that you can do with these, and I'll actually label this as another step here, step 3, is to check your solution using your last free body diagram. All right. If you do this in this way, and you solve for your external reactions first, and then you go through and use these things, you will always have this extra free body diagram you can do to help check your solution. So let's go ahead and do that. We're going to do a free body diagram of the joint at A. All right, so there's the joint, and that joint has several forces acting on it. We would have a tension that we'll call TAD. All right, we do know the value of that. We have a force here that we will call TAB. We have a force over here, RAX, and didn't really talk a lot about that earlier, but we'll talk about it here in just a second. And then we have this force here, RAY, and so what I'll do here is I'm going to label the things that we know here. TAB, this is equal to negative 8.33 pounds. TAD, let's see, that one was equal to 6.67 pounds. All right. RAY was equal to 5 pounds. And RAX, actually, we didn't really do this, but if you had done a free body or on the free body diagram that we did of the entire structure, if you had done a sum of forces in the x direction, you would have found that RAX is just equal to 0 because we have no external forces acting in the x direction, and so RAX doesn't have to react against anything. All right. So here, now that we've got that, we can do a sum of forces just like we do on everything else. We do sum of forces. We'll just start in the x direction here first, and when we do that, we'll find here that we have TAD, which was 6.67 pounds, acting to the right. Then we have TAB, all right, and that was actually negative 8.33 pounds, and just getting the horizontal component of that, we would have to multiply it based on this slope over here of 4 to 3. We would have to multiply that thing by a value of 4 over 5. All right, and it looks to me like that's the only values that we've got there. All right, and set that equal to 0. If you actually do this calculation out and you multiply 4 over 5 by that 8.33, you will find here that you end up with a statement that 0 is equal to 0, which basically means that you have checked your answer using an independent check, and so that's a confidence builder that you did everything right. All right, and then over here you can do the same thing. We can take the sum of forces in the y, and it ends up looking very similar. Here we'll have RAY of 5 pounds acting upward there, so we'll put that in 5 pounds. And then TAB has a vertical component there, and you can find that by taking minus 8.33 pounds times 3 over 5. That gives you the vertical component. And those are the only ones we've got. It's equal to 0. And here again, we end up with 0 equal to 0. And so that's just another good check. So by doing this, you can actually give yourself a lot more confidence that you didn't make a mistake somewhere.